Good day and welcome to Africa Teen Geek. This is the STEM Digital School. Welcome to Africa Teen Geek. This is the STEM Digital School. If you have just joined into this classroom, this is the grade 11 Physical Sciences. This is the grade 11 Physical Sciences. Today is the 27th of July 2020. I am your teacher. My name is Nokulego Matondo, and I am your teacher for grade 11 Physical Sciences. Today, however, we've got an interesting topic that we're going to be working with. As you guys remember, we've been working on calculations these past few days. And before that, we did all the theory for electricity and magnetism. And then later, we went back to go and do all the calculations that are done. We've done almost everything now. We just left with the series parallel circuits and the power. So, guys, it's been a great journey. As you guys remember, on Thursday last week, we had some assessments that we did, and I hope that everybody did well in these assessments. And as for the memorandum that we did on Friday, we couldn't finish everything on Friday because, even though we're doing a lesson, we still need to explain how the answers were gotten and the procedure on how to solve it. So that sometimes tend to take a bit of time for us. So that is why we need you all to be in line and participating. Thank you guys so much for joining this classroom. I just want to remind you guys that in this classroom, I work on the Siavula textbook and the Oxford Successful, but mostly the Oxford Successful. If you do have either of these textbooks, you can use them for this classroom. And guess what? Reminding you again that you can get it absolutely free on Snaplify if you'd like to to be part to get a mass number of textbooks that are absolutely free until the 31st of December 2020. You guys can um, you guys can register with Snaplify. You can do it on your phone, you can do it on your PC, you can have your textbooks in your phone everywhere you go. I mean, that is absolutely incredible. So you guys can try and get Snaplify and download not just for physical science but for all your other subjects as well. So that is something that is important that I feel you guys need to know as well. So guys, let's start with our previous question and finish off our memorandum for the test that we had last week. What I can It's the application of the Ohm's law, right? We last did question 125, but we couldn't start with number 6 because our time had already run out. Okay, so 6.1, application of Ohm's law. Okay, so now as you guys can see what we have there, we've got a series parallel circuit. Well, I kind of put that in the test just to test if you guys have learned to differentiate between a series circuit and a parallel circuit. But we're going to do more about that today, and I think it will become much more easier after this lesson. But I just threw it there for you guys to see if you guys know the difference between the series and the parallel branches. Okay, so the circuit below consists of a 6 ohms and 15 ohms resistor connected in parallel and an unknown resistor R, which is in series. So these are the two parallel resistors, and this one is the series to the parallel branch. So they say an ammeter, which is this one. Guys, remember the difference between an ammeter and voltmeter. An ammeter is always placed in series to the conductors, right? And the voltage is always put in parallel across whichever branch that you would like to calculate. And another thing that I want to remind you guys that an ammeter does not put in the current in the circuit. What it does, it just shows you basically it translates in amps, right? And in this case, same with voltages. This one, it just shows you how much voltage is in the circuit. It's a mere instrument, nothing more, nothing less. Okay, so we've got a high resistance voltmeter, which is the one that we have here across this R resistance, and a closed circuit. This is a circuit that is closed. These two dots, they indicate that the circuit is closed. If these two dots were there, but you had a line that is open there, it would mean that our circuit is open, right? So the resistance of a battery and wire can be ignored. So here, basically, just calculating what is asked. So they say now the total power dissipated in the parallel part of the circuit is 50 watts. Okay. Sorry about the numbering there, guys. You know, teaching and IT. But nonetheless, 6.1.1 says define the term power. You know, we have power in all our phases where we need to do calculations. And every time they mean different things depending on what part of the topic you are dealing with. Okay. So in this case, power is the rate at which work is done or energy is transferred. This is the general definition of power. Okay. So we get to calculate power wherever we work with problems with circuits. Okay. So let's move on to 6.1.2. It says calculate the effective resistance of the parallel combination. Where's our parallel combination, guys? This is our parallel combination. So now they want to know the effective resistance there. So what do we have to do? We know that now we have to use the parallel equation, the parallel circuit equation. And we already know that that is equals to R1 over R parallel is equals to 1 over R1 plus 1 over R2. And in this case, we've got these numbers respectively. So let's see how much we get as our, here we have it. It's 1 over R parallel is equals to 1 over R1 plus 1 over R2. Then you substitute these two. But now you need to change this into a common denominator. So you find yourself a common denominator there, or you can times this 2 by 8, times here by 15, and times here by 6. And you will get an answer for that. And after that, you're going to cross multiply the answers for you to have R parallel as the subject of this formula. Now that is the first option. Here in the test, they basically showed two options that you can do. Here, where you can say R parallel is equals to R1 times R2 divided by R1 plus R2. Okay. And there we have it. And that's where we get our R parallel. I think option 2 is much more simpler because now you don't have to worry about having to cross multiply and do all of that and make mistakes. Because you know, when you're writing a test, there's always the panic mode and the pressure of time that you have, and you do not have time to, you know, discriminate your information thoroughly. So that's why I prefer to use this one right here. It's much more simpler. Okay. Let's move to 6.1.3. 6.1.3 says calculate the potential difference across the resistors in parallel. So now, remember we spoke about it, equivalent resistance. Basically, in this case, now that we've calculated the resistance in parallel, it means that we're going to have an equivalent resistance right there, which will be 1 block. So which means this one is now going to be, this R equivalent is going to be series to this R now. Okay. And then you can do that on your worksheet. It's always best for you guys to jot it down, whatever problem that you have. So what you do, you draw now the circuit with the parallel branch already having one value of ohms. Okay. And what we do, therefore, now you can calculate the voltage across that parallel branch. Okay. The potential across the resistors in parallel. And then let's see how you can do that. Okay. So what do we have there? Remember, they've given us the power, the effective resistance, the potential across. I'm just trying. Oh yes, they've mentioned here that the power dissipated is 50 watts. Okay. So which means that now we've got two given. We've got the resistance, which is the R parallel, that is right there, and we've got the power, which is in P. The power is what was given. So guys, make sure that you're always able to find what is given. Okay. Why are we using the power equation here? Because we do not have the current. So unless you want to go back and calculate the current and do a long procedure, sometimes you need to check what is given. That's why I always say to you guys, whenever you get a problem, especially when that one that has to do with calculation, it's always important that you write down what is given. Okay. Once you see power, you know that somehow power is going to be involved in your calculation. And remember, earlier lessons, we did have our power triangle that we were using to calculate our power, voltage, or resistance. So this is a good equation because now you don't need to have current for you you to calculate the voltage, because we have the power that is given and the equivalent resistance that we calculated over there. And therefore, our voltage will be 14.65 volts. Guys, please do make sure, I remind you guys as always that you need to make sure that you've got all your questions, you do all your values, and what's great as well that you can always draw your triangle in your papers so that you know which one can work with which one. Okay. So now let's go back to the next question. Okay. I'm just trying to get to the next page. As you guys know, sometimes you've got a problem with the slides going slow. So now we move to 6.1.4. Okay. So there, okay. So now we have 6.1.4. They say that calculate the current through resistor R. Okay. It says calculate the current through resistor R. So where's our resistor R? This is our resistor R, right? Our resistor R is a resistor that is in series to the parallel branch. This is our resistance that is in series to our parallel branch. So as you can see already, we've got a voltmeter that is across it. So basically this voltmeter is what we are calculating, what the voltmeter reading is basically. So that's how we get to know the voltage. We've got a voltmeter, or you can calculate using the values of what you already have. So let's see how to do that. So it says here, again, we've got options, right? Because we're looking for the current. And what we know is that, remember, the voltage in series, the voltage in series, it's a voltage, the resistors in series is a voltage divider, okay? So we go back and we see what we have there. So now it's going to say resistance is equal to voltage divided by current. But remember, when our when our when our voltage when we have a series branch, what happens is V1 is equal to V2, which is equal to V total. So the voltages are the same. They're the only thing that would be different would be the current. Okay. So always remember the whole current divider, which one is dividing and which one stays the same. So here we use the voltage because the voltage stays the same in both series arrangements. Okay. So now our current is going to be 3.41 amps. But now there's also another option where we could have used our power equation because we've already been given 50 watts. We just add the voltage because remember, voltages in series are the same in both sides, okay? So it's going to be 14.65 and that's going to be divided from the 50 and that will be 3.41 amps. And then we've got also option 3 once again. If you feel like you're not sure what voltage to use because you just want to use what is given and what you are absolutely sure about, you can use the P is equals to I squared R and you can use the 50 watts and you can use the resistance that you calculated for your parallel branch. Okay. And that will give you 3.41. Okay. And then there's also another option, which is option 4, where, oh, this one is quite a long option. Let's just use this option. Okay. Just work on learning these 3 options and seeing how you can do them, how you can find one answer using different ways of calculating. Okay. So now we come to, they say now the switch in the circuit is now open. Okay. So they want to know on 6.125, how will the reading on the voltmeter be influenced? Choose increase, decrease, or remain the same. It will decrease. Okay. So basically, the voltage will decrease. Guys, if you do have questions, please do send me a chat so that I can try and explain wherever it is that you guys are getting stuck. Because the main important thing here is for you guys to learn and for you guys to understand. So that's the main point. Okay. So I hope that everybody did well in their test, and this was quite easy for you guys. So now we're moving to the lesson of the day. Today we're going to be doing a lot of parallel series resistors or series parallel resistors. Okay, so this one here, what I have here is a typical example of how a series parallel circuit looks like. Okay, and the current flow in each. Okay, so it says here the EMF is the maximum voltage of the battery. This is a battery, right? And maybe you've got, it's a 50-volt battery. I'm just making a typical example. That is the maximum the battery voltage can send through into this circuit. So we measure EMF when the battery is not connected to the circuit. Okay. So you can be able to measure the value of your EMF if it's not connected. What does if it's not connected mean, guys? It basically means what this problem has given us right here. You see here, a circuit is closed. It means that the circuit is operational. But once it opens there, it means that there is no more current flow in the circuit. And that's exactly what is being explained here. That when the battery is connected, when you measure EMF, when the battery is not connected to a circuit, so which means your switch here would be open, which means there is no current flow. So when a battery is connected to a closed circuit, the voltage becomes usually very low. So this is because not all of the energy of the chemical reaction transfers to the circuit. So because it's a battery and it's a mechanism of storing energy, not all of it gets dismissed out of the circuit. So the voltage is the battery voltage or the terminal potential difference. So potential difference and voltage, remember guys, it means the same thing. So the terminal potential difference is the voltage of the battery or energy supply connected to a closed circuit. Make sure you understand this, closed circuit. Okay. So a battery in this case is the source and is the one that is supplying energy to the circuit. So we calculated when it is not connected to the circuit. Okay. I hope that that makes sense to you guys. But you'll see, guys, we are going to have some examples. So how do we solve the series parallel circuits? How do we get it right to make sure that we do the correct calculations so that we can get the correct answers? So it says the following hints will help, but remember, the order of solving these problems may differ from problem to problem. You're going to see just now when we start doing our problems that they differ. It's not always the same procedure, but this one that I have right here is just a standard hint that you guys can use to understand the series parallel circuit. So it says for the first one, find the equivalent combined resistance RP if resistors are connected in parallel. So it's always advisable that when you have a parallel circuit, the first thing that you calculate is the parallel branch. Why? Because the parallel branch is so complicated. It's a 1 over R where you have to times the 1 and the 1. So it's much easier for you to try and calculate that one first. And then after that, you find the equivalent resistance R circuit of the circuit. So which means that now after you have your parallel branch, you're going to have your equivalent parallel branch. And from there, you're going to add it with your series resistance. And then you find your resistance, the R circuit, which is the total resistance. So now you calculate the current in the series part of the circuit. To do this, substitute the equivalent resistance of the circuit and the terminal potential difference of the energy source into the equation for current, which is V over R, because it depends what they want. Sometimes they want the voltage across, sometimes they want the current across, but the resistors will be done because you have already calculated all of them and you've got your different circuits that indicates, okay, this one is the normal circuit. The second circuit will be the one where is the RP plus the individual R series ones that you have calculated. And after that, you can calculate it into one branch and you have one resistance equivalent circuit. So you only have one block that shows resistance, then you're going to have your source, and then you're going to have your connection. Okay, so here's the following equation to answer questions about parts of the circuit. Okay, so this is our Ohm's law triangle. I decided to put it here just to give you guys a reminder. Remember, guys, when you calculate the voltage, it's going to be current over resistance. That's why I say always make sure that you draw your triangle. Just now, you get confused and you think current is equal to voltage times resistance. It's very important that you always have a little triangle to remind you how the equation works. Okay, so for voltage, it will be I times R. For current, it will be V over R. So you make sure you make use of these lines. So make sure, guys, you calculate it in that way. If you are having problems and still want me to explain something, please send me a chat and I'll do that very fast. Okay, so be careful to substitute the correct values into the equation, because sometimes I know it gets hectic in a test and you find yourself not remembering what the Ohm's law triangle looks like. You end up not remembering if the current is perpendicular to the voltage. What does that mean? If the current is inversely proportional to the resistance, what does that mean? Those are things that happen. So make sure that you get that right. So for example, if you are across a resistance, it's not going to be the same as the voltage across the entire circuit, depending. But in this case, because we've got parallel branches and series branches, we know that our voltage is going to be divided if they're in series, right? They're going to be divided amongst each other. So you do not use the voltage across the whole circuit. Make sure that you selectively choose the one that is across that specific resistance. Okay. So now we're going to do a quick example. So our example says, use the information on the circuit diagram in figure 2 to calculate the following. Okay. Number 1, we're going to calculate the equivalent resistance of the circuit. Number 2, the reading on the ammeter. So this is our instrument right here. It's the ammeter. We need to know what is the reading on the ammeter. And then now we're going to, number 3, we need to calculate the current through this parallel branch of the resistor, right? And the voltage across the 2.6, which is the series branch, across this series resistor. Okay, so this is all questions put in one. So this is the simplest kind of parallel series circuit that you can find. You're going to see, we're going to do another example that is much more complex than this one, but it's good, guys, because we are preparing you to get to understand how to work out the series parallel branches. So method 1, method of the part 1, to calculate the equivalent resistance of the circuit. The first thing that we're going to do, we're going to where's the mouse? We're going to try and change this into one equivalent resistance branch, okay, so that it can be in series to this one, because it's kind of difficult when it's standing like this. So we're going to first calculate our parallel branch. Like I said on the first step, it's always easier when you start by calculating the parallel branch and then you add that to the series branch. So we're going to use this one. It's going to be 1 over R parallel is equals to 1 over R1 plus 1 over R2. Or you can say R parallel is equals to R1 times R2 over R1 plus R2. That one is also very simple, okay? And then from there, we're going to get our R parallel. And you see, now we've got our R parallel as an equivalent resistance branch right here. It's going to be 2.4 ohms. So now it's in series to the 2.6 ohms. So now we still have resistances in series. So which means that we need to add them together until we get our equivalent resistance, which will be a 1 block over here. So how do we get that? In series, we said R series is equals to R1 plus R2, and that will give us our 5 ohms. So our equivalent resistance of the circuit is 5 ohms. Okay. Okay, seems that I forgot to write to take in the other steps of this one, but it's fine, guys. We'll go back to it. I'll just show you guys on the textbook, as this is an example that I got directly from the textbook. So we'll get to check it out later. Let's just move to the other problem. As long as you understand how this is done, then it's all good. Okay, but let me see if we can check this out now. Okay, no, it's fine. We'll do it again if we still have some time. We still have some other problems that are pressing. So check this one out. It says here, find the equivalent resistance are equivalent for the following resistor combination. Yo, guys, I know this is complex, but I wanted to test you guys and I wanted us to work through it so that you can see how simple it can be to solve and the parallel series branches. Okay, so if you check here, if we had to minus out these triangles and turn them into proper circuits that are square. So if you have these two nodes, you know that these two up here are series and they're parallel to this one, and this one is is um is parallel to this one, but these two are also parallel to that one. So I just want to show you guys how you can solve an equation like this. So again, at first glance, this resistor ladder network may seem like a complicated task, but as before, it's just a combination of series parallel circuits that are connected together. So starting from the right-hand side, which is from this side, we're going to start solving this combination, okay? And using simplified equation for two parallel circuit resistors, we can find the equivalent resistors of R8, R8, and R10. So here we're going to use the series partner, and we're going to call this series branch RA. Okay. Okay, I'm just trying to go to the next slide. Okay, so here we have it. If you check this one out now, this is our parallel circuit. This is our parallel circuit, right? We're starting with the first part. But this one, our RA will be our series branch, right? So what are we going to do? We're going to say RA, which is our first series branch, is going to be R9, which is this one here, is parallel to, this will be parallel to these two, right? And remember what I said you can say R1 times R2 divided by R1 plus R2. So in this case, we've got 8 plus 10. So the 8 plus 10 is these two series ones right here. And you times that total series branch by the parallel branch. And then you divide that by this one. You can also put a bracket here if you want to understand why all of a sudden at the bottom they are all added together. This one would have been in a bracket, but in this case it was not necessary because it would have meant the very same thing. Okay, guys, please, in this part of the explanation, wherever you get stuck, just send a chat so that I can explain, because this one is a very much more complex diagram. Okay, so here we have it. We have our 6 times this this series branch right here, and divided by the sum of all of them, and that will give us 4 ohms. Okay, so what does that mean for us now? It means that we've got an RA equivalent of these two branches right here. Okay, these two are series and parallel to this one, so we name them RA. So with R7, oh, okay, okay, I'll explain again RA. So what is happening here? Let me just go back. Okay, doesn't want to go back, but I can still explain it like this. We've got our RA, right? Our RA is a name that we have given these parallel branches. This triangle here, these two here are parallel to this one here. If you can see these nodes, they actually determine if your branch is series or parallel, right? So these ones, these two, this is a series branch. If you add them together, they become in series to one another, okay? But here, because of these dots right here, it shows that now they are parallel to this one. Because if you had to extend this and make it a more rectangular circuit, these two would be right here, and the lines would be here, and it would still be parallel. These nodes here, they explain everything. They tell you whether a series, this is a series branch um or a parallel branch. So whenever you see these nodes, it means that here it's series, but it's parallel to this one here. So as you can see between these two, we do not have these nodes here. Okay. So if we do not have this node here, it means that these two are in series. Okay. So if we had to write it down, if we had to separate it, this part here, this 8 plus 10, it would have been, this will be R1 and this will be R2. Okay, so this will be these two series branches would be R1 and this would be R2. So what we know about our equations is that R parallel is equals to R1 plus R2. But if you check here our R is equals to the sum of these two. Okay, I hope you're getting it. It's the sum of these two, and that these two are parallel to this one right here. So that's why here we've got R9 times the branch of the series branch is R8 plus R10. And that will be divided by, hence I told you that earlier on, here it would have been, it could have been a bracket, but they just left it open. Okay. And you remember from your bottomless rule that you first sort out what's in the bracket before you go to the outside. Okay. So it would be R plus 8 times this R9. I hope that you really get it. Now, if you do, please just let me know. Okay. So now let's move on. So now that you have RA, the total resistance now will be RA plus R7. So this is our RA, right? This whole branch is RA. But if you check here, it's in series to this one, okay, to this R7. They are in series together. So if they're in series, it's going to be this R7 plus this R8 branch, okay? And this will be just as it's shown. Okay, so you see now we have broken it up, right? So we've got RA and we've got our R7. Remember, I told you can always extend it to a square form because sometimes the triangles can be very tricky, but this is what you will have. So now these two will be parallel to this parallel branch here. So you see, as we go along, we are closing down the circuit. We are making it much shorter and much more equivalent. Okay. So here it's going to be this R1, which is R6, will be parallel to this two branch. So this RB branch is going to be RA plus R7. okay? And these two will be parallel to the R6, which is what we have here. So you're going to say times that by these two, the sum of these two will be multiplied by the R6, and you divide them by the sum of each individual. But like I said, this could have also been made as a bracket, but it was unnecessary because it all means the same thing, just for explanation purposes, okay? And therefore, we're going to have our 4 ohms. So which means that now we've got our RE. So this branch right here has been solved now. So it's very important that you do these steps one step at a time. Okay. So now RB is in series with R5. Here is R5 here. So you see this RB is an equivalent of all the other triangles that we had before, right? So now it's made one equivalent to RB. So now we need to move on. So now we know that our RB is in series to our R5, and the sum of these two are parallel to our R4. Okay. If you're still getting confused, just let me know. Okay. So now we're going to have the same thing. So you see, we're just repeating the same procedures in different ways. So that is what is happening. Okay. So now these two will be in parallel to R4. And that's what we have right here. It's going to be R4 times the sum of these two. And the sum of these two divided by the sum of all the individual ones. Okay? And this will be a resistive value of 8 ohms. So we're going to have a total of 4 ohms. So RC is equal to RC, and therefore the total resistance will be R3 plus this RC circuit, this branch that we've calculated. And this is how that is going to look like, okay? So this is the RC branch, and we're going to add it to the R3 that we have on the side. And this is going to give us our 4 ohms. Because it's going to be this R parallel to the sum of these two. So you see, we just keep repeating the steps like we did from the start of our triangles, right? And that is going to give us our 4 ohms. So RC is equal to R1, and therefore the total resistance will be RG, which is this whole branch, plus R1, and that will be 4 plus 6, and that will give us 10 ohms. So you see, guys, then the complex combinational resistance matrix above comprised of 10 individual resistors connected together in the series parallel combination can be replaced with just one single equivalent resistance of the value of 10 ohms. So when solving any combinational resistance circuit that is made up of resistors in series and parallel branches, the first step we need to take is to identify the simple series and the parallel resistor branch and replace them with equivalent resistors. So this step will allow us to reduce the complexity of the circuit and help us transform a complex combinational resistance circuit into a single equivalent resistance, remembering that the series circuits are voltage dividers and the parallel circuits are current dividers. Okay. So, however, to calculate a more complex keypad annuator, the resistive branch matrix, which cannot be reduced to simple parallel or series circuits using the equivalent resistance, require a different approach. So these are ones that you're going to see later on in your grade as you move up. Okay. So this one is our homework for today. So this is our homework, guys. Can you please just take a snapshot? We're going to be doing this homework starting from tomorrow. I don't know how long it's going to take because there's quite a lot of problems, but I want us to do them all, guys. Time is of the essence, but what's important is for you guys to understand the procedure, how to do them, how to get in the mind of doing them. So I'm just giving you time to take pictures of your homework. Okay, this is our number 2. Please take a picture. We're going to start with them tomorrow before we move to our next lesson. Okay. So here is the number 4. Okay. Thank you guys so much for a beautiful lesson. And thank you for participating as well. And I hope that the gentleman that sent out a query has been sorted and understanding. But if you don't still understand, you guys can send me a chat on